Is this for the benefit of whatever electrical engineers we have?
Not really. Just a good example. Just a good example. All right, good morning, everyone. So, yesterday we went through what inductors. So this is for self-inductance again. So we said that the inductance of a inductor is then equal to the number of loops times the flux through each one of those loops divided by the current. So this is our definition of self-inductance. And I don't know why that guy's not coming up. Play with that in a second. Again, while this guy is charging up, there is a potential difference across the sky. So there's a potential drop from this side to the other side. So this is point A, this is point B. There's potential drop. So the potential at A is greater than the potential at B, such that the potential drop in this case, again, is our back EMF. So this is given this way. And again, once the current reaches maximum current, so the derivative goes to zero, then this thing acts just like a straight wire. So there's no more potential difference across there. Again, the energy stored is 1/2 the inductance times the current squared. So again, my battery has to do work over this back potential or this back current to get it to reach maximum charge. And then the energy density, which is the energy stored per unit volume, is given that way. So let's do an example of this. Let's see how to actually calculate the self-inductance. And this guy's not working. Let me play with this for just a second. Run through. But anyways, as it's drawn on the board here, all it wants us to do then is find the self-inductance for a coaxial cable. You gonna work? Not gonna work. Okay, so where we have an inside cable in this case, which has current, say, running in this direction, we have the coaxial part, which has current running in the opposite direction, so that the total net magnetic field is equal to 0 by Ampere's law on the outside. That thing's not working, so I'll just get rid of that. Screw it. So great. So once we find the self-inductance for this guy. So good. So what do we know? We know by right-hand rule number 1 that we put our thumb in the direction of the current. Our fingers are going to curl around in the direction of the magnetic field, which means in this case, our magnetic field will curl around in this direction. Right? So let's look at the flux. So my flux then is equal to, again, by definition, the integral of B dot dN. Now, every time we've looked at flux so far, the magnetic field has been constant over position. But in this case, that's not true because we know the magnetic field of the wire is equal to mu naught I divided by 2 pi r, which means this guy is spatially dependent. So all that means then is that this point here, where the magnetic field is going into the board, versus this point over here, where the magnetic field is also going into the board, the magnitude of the magnetic field is less. Which means that our flux in this case, we're actually going to have to do the integral. Okay. So let's look at the flux then. So what we want to do is look at the flux through some differential area in this case. So let's draw our differential area. We're going to draw some strip across here. Okay. So this is my differential area, where this thing then is going to have some length of L to it. It's going to have some thickness of dr, and this is going to be at some radial distance of, let's say, r in this case, from the central wire in this case. Everybody's doing okay? Now, because my magnetic field is into the board, that means I'm going to take my differential area also into the board. So my dot product simply is going to become 1. So it's going to be my area vector, in this case, my differential area vector. So this guy then is going to be equal to the integral of BdA. Now, B, we know, is a wire. So this is going to be mu naught I over 2 pi r. My differential area then is simply going to be the length times the thickness. So this is going to be L times dr. Okay. As far as our integral is concerned, L is a constant, 2 pi is a constant, mu naught's a constant, and I is a constant. So let's follow this out. So I'm going to go mu naught I L over 2 pi integral of then dr over r. And then finally, I need my bounds of integration. So in this case, we're going to integrate from the outer radius of the inside to the inside radius of the outside, which means they're going to integrate this guy from R1 to R2. Okay. C'est bon. What is the integral of 1 over r dr? Natural log of r. So this guy then is going to be equal to mu naught I L divided by 2 pi times the natural log of R2 over R1. So this then is my, excuse me, magnetic flux. So then plugging that into my inductance equation here, we're now going to write this then as my inductance is going to be the number of loops times my flux divided by my current. In this case, of course, there's only one loop, right? So I have one loop. In this case, the current's going here, coming back in this direction, coming back around. So that's just simply one loop. So n in this case is equal to 1. So it's going to be this guy divided by the current. But what's going to happen to the current? Guys cancel, right? So this guy's just going to be equal to mu naught I. Oh, sorry, no I. Mu naught L over 2 pi times the natural log then of R2 over R1. So this then is my self-inductance for this coaxial cable. We're doing okay? Not too bad. Nice and easy, right? So for different geometries, we would just do that integral over different ways. So if I had an inductor like this guy, a solenoid, in this case, we know the magnetic field is simply constant anywhere on the inside, which means this would just be B times A, because it's constant anywhere on the inside. Or any other type of geometry, we either have to do the integral or not do the integral, depending if it's spatially dependent or not. But okay? Not too bad. All stuff we've seen before. So cool. So next thing we're going to talk about is, let's now start taking these inductors, which are now electrical elements, and put them into circuits. So let's start looking at inductors inside of circuits. So let's place these guys in circuits. So place them into circuits. So specifically, we're going to look at what's known as an LC circuit, which means that we're going to have an inductor with a capacitor. And we're also going to look at LR circuits and then LRC circuits. So let's start with our LC circuits first. So in this case, we're going to take a fully charged capacitor. So here's going to be my capacitor. This thing's going to start off with some initial amount of charge. So let's say this side then is positively charged, and this side then is going to be negatively charged. We're now going to connect that guy in series into an inductor. So here's my inductor. That's this guy. So here's my inductor with some inductance C, or sorry, L, and then this guy's going to have some capacitance of C. Is doing okay? So let's talk about what's actually going to happen. So here, this guy comes in fully charged, but does he want to remain fully charged? No, I have positive charges on this side, negative charges on this side. So what does it want to do? What's going to happen to the charges? What does it want to do? What are the charges going to do? Right, so these guys are just simply going to rearrange themselves until it neutralizes, right? So what's going to happen then is these positive charges will now start to move, because again, Benjamin Franklin. So we're going to say these charges are going to now start to move. So the charge here is going to decrease while what? We're now going to start building current through our system. So these charges are going to start to move. We're now going to build current going through this system in this direction. Okay? Now, initially, at t is equal to 0, what happens in this case then, again, is our charge is equal to the initial charge, and the current is equal to 0. Right? Now, as time goes on, what's going to happen to the size of the currents? It's going to increase, and what's going to happen to the size of the charge? It's going to decrease until I'm going to get to a situation where, let's redraw this guy. Now we're going to have 0 charge. So both of these two plates will be 0 charged. But now I'm going to have maximum current running through the system. Okay? But again, I have positive charges moving through here. So I still have positive charges flowing through the system because, again, I have maximum currents, which means what's going to happen as these positive charge particles are moving? What's now going to happen to this plate? Going to accumulate all the charge. So this guy's going to become positively charged. This guy's going to become negatively charged. So at some time iteration later, what's going to happen then is what? These two guys are going to switch sides, which means that, use my same color scheme as before. This side here is going to become positively charged. This side then is going to become negatively charged. And when this happens, again, my charge then is going to become my maximum charge. My current then is going to go to 0, where here my charge was equal to 0, and my current was equal to the maximum. Was okay? What's up?
Why does it like completely reverse charge?
Oh, because as the charge is moving through here, there's nothing to stop the charge. So the charge has to keep moving so that it's going to build up on here, right? Which leaves this guy then negatively charged as all these positive charges keep moving.
So, why don't they stop once there's like a neutral amount of charge on it?
Oh, because now I have maximum current flowing through the system.
Okay.
Okay. So keep that in mind. We'll come back to that in a second.
Okay. So
Okay.
we'll learn why it keeps on flowing.
We'll learn why it's going to keep going. Exactly.
I was like, that doesn't make sense because it makes more sense to want to become neutral.
Well, right. But again, when it's neutral, I have maximum amount of charges which are moving. Right. But there's nothing to stop the charges from moving.
Okay.
Right. So even though these guys are discharged, so I have zero amount of charge on here. But again, since my current now is maximum, I have a maximum amount of charges moving, but there's nothing to stop them inside of the inductor. There's no resistance or anything causing them to stop. So they just have to keep moving until they overshoot, and then we'll end up accumulating onto this one.
Okay.
Does this make sense? Everybody kind of see where we're going? Cool. So at some time later, again, what's going to happen then is these charges now, again, don't want to be here, wants to be neutralized. So these charges are going to start moving in the opposite direction. So all of my positive charges now are going to start moving in the opposite direction, which means we're going to build up current moving in this direction, which means that some time later, what's going to happen? So we have our inductor. This thing is going to reach zero charge. And now I'm going to have maximum current flowing in this direction. So at this point in time, again, my charge will then be equal to zero. I'm going to have maximum amount of current flowing in the system. And then what's going to happen? These maximum charges are going to keep flowing, and now they're going to become this situation again. And then it's going to do it all over again. What is this? What is this? It's what? It's AC. Good, because it keeps going back and forth. It's an AC circuit. Well, let's go back 1,000 years ago. What's that? It's a harmonic oscillator. Fantastic. We have now created a harmonic oscillator, right? Told you, this will never go away. Life is crazy. So even in electrical circuits, we have a harmonic oscillator. Right? So again, as long as this thing starts off maximally charged, it's going to harmonically oscillate back and forth, because just like a harmonic oscillator, where this is my equilibrium position, again, when I get out here, I have maximum amount of acceleration. But by the time it gets to the origin here, right, it now has maximum velocity, which in this case is maximum current, but there's nothing to stop it. So it has to keep accumulating onto the other side because there's nothing there to slow it down or stop it. So in this case, it has to go back and forth under harmonic oscillation. And that's all this thing becomes is a harmonic oscillator. Beautiful. So an LC circuit is simply a harmonic oscillator. So let's analyze the system and let's actually show that. And we're going to do that by using Kirchhoff's rules. So let's talk about Kirchhoff's rules. So let me redraw my system here. So here then is my inductor. Here then is my capacitor. And let's do it this way. So let's say this thing has positively charged here, negatively charged here. And this is going to have some currents running through it, or my current then is going to go, in this case, in this direction, because my positive charges are moving this way. So at this moment, this thing has just some charge Q, and this has some current of I. It's okay? Now, let's start off at some point. Let's say this point's here. So using Kirchhoff's rules, we would then come up in this direction across my capacitor, but I go from the negative side to the positive side. So would I increase or decrease potential? So meaning, would I have more potential on this side or less potential on this side compared to this side? More, right? So I'm going from the negative side to the positive side. We know the negative side is the low potential side. Positive side is the high potential side. So in this case, we're going to get a plus Q over C. Now, in this case, we're going to go across the inductor in the same direction as the current. And as we saw, that's going to give me a potential drop, where that potential drop then is going to be minus L times di dt. And now we're back to the same point. So that's going to be equal to 0. Okay. Everybody's doing okay? Now, from here, We know, though, the current is related to the charge by the time rate of change of the charge. Okay? So in this case, we can now rewrite this entire thing in terms of the charge by noting that our current is equal to the time rate of change of the charge. Now, in this case, as the charge is decreasing, what's happening to the current? It's increasing, which means that we have to actually throw a negative sign on there, because as this guy is decreasing, this is going to be a negative. But this guy is increasing, which means we need an extra negative to make that guy a positive. Okay? So as this guy gets smaller, this guy is getting bigger. So let's plug that in here. So finally, this guy's going to become L. Second time rate of change of the charge plus then Q over C is equal to 0. Now, we said before was that we want to get it in the form that the acceleration then is equal to minus whatever shows up in front is then the angular frequency squared times then the position. In this case, the second rate of change of the charge is the same thing as the acceleration, and then the charge itself is the same thing as position. So let's make that look like this. So first of all, I'm going to divide both sides or the whole thing through by an L. So I'm going to get a D second time rate of change of the charge squared plus then 1 over LC times the charge is equal to 0. Or let's subtract that guy from the other side. So we then get that the second time rate of change of the charge is then equal to minus 1 over LC times the charge. Okay? Now, going back to what we did 1,000 years ago, i.e. to here, we simply match these two things together. Acceleration on the left-hand side, position on the right-hand side, whatever shows up in front of that between the negative sign is the angular frequency squared by definition, which means in this case, my angular frequency squared is simply 1 over the inductance times the capacitance, which means my angular frequency is 1 over the square root of LC. Okay. So indeed, this thing is a harmonic oscillator where the angular frequency is simply 1 over the square root of the, capacitance times the inductance, which means our charge as a function of time is equal then to whatever the initial charge was, Q0, times then cosine of omega t plus our phase factor. This is then the charge as a function of time. What's that? It's the amplitude. Yes. Yeah. It's the amplitude because it's the amount at which this thing starts off at. Exactly. So the initial amount of charge is my amplitude. Absolutely. From here, we can then find the current as a function of time by taking the derivative of the charge and then throwing a negative sign out in front of it. So in this case, what's the derivative of cosine? Negative sign with the negative sign, so it makes it a positive. So this is going to be the same thing then as Q0 times omega times sine then of omega t plus my phase factor. So this says then that the amplitude of the current is then equal to the amplitude of the charge, i.e. Q0 times the angular frequency. So I can then define this then as my I0 times sine of omega t plus the phase factor. Everybody's doing okay? Back to haunt our dreams. Okay. Now, what does this say? This says then that's what the current is out of phase with the charge by 90 degrees, which means that when the charge is maximum, the current is 0. When the current is maximum, the charge is 0, just like we said previously, right? But notice that the total energy is actually equal to a constant. Okay, so let's talk about that. So let's talk about this. So first off, let's plot these two guys. So let's plot them. So here I'm going to plot this such that my charge is in purple and then my current is in blue. So in this case, this thing's going to start off at maximum amount of charge, Q0, and then this guy's going to oscillate as a cosine curve, right? So this is my charge as a function of time. For my current, this is going to be my blue. This thing's going to start off at 0, reach maximum when this guy is 0, go to minimum here, and then again reach maximum at this point, and then go to 0 at this point. So this then is going to be my current as a function of time. Or, as Andre said, this is actually an AC circuit, right? Alternating currents. So good. So let's talk about the total energy. So my total energy then is going to be what? The energy, in this case, my total energy, so let's do it this way, U total is going to be equal to the energy of the electric plus then the energy of the magnetic. Okay? Now, because this is a capacitor, we know the energy of the electric is going to be 1/2 the capacitance times then the potential squared plus 1/2 the inductance times the current squared. Or since we don't know the potential, we do know the charge. We're going to write this then as 1/2 the charge squared divided by the capacitance plus 1/2 the inductance times the current squared. Everybody's doing okay? So all we're going to do is we're going to take these two things and square them. So if I do that, this guy's going to be equal to 1/2 Q0 squared over the capacitance times cosine squared, parentheses, I'm not going to bother right now holding them, plus my 1/2, my inductance times my current squared, which I'm going to write in terms of the charge. So this is going to be my charge squared times my angular frequency squared times then sine squared of parentheses. Is doing okay? C'est bon? I'll take that as a maybe. Now, what we also know, though, is omega, or at least omega squared, is 1 over LC, which means if I replace this then with 1 over LC, the inductance is going to cancel. So this becomes Q0 squared over C. This is also Q0 squared over C with a factor of 1/2 for each one, which means I can rewrite this then as 1/2 Q0 squared over C times cosine squared plus sine squared. But what's cosine squared plus sine squared? 1. So this means that my total energy is simply equal to a constant, which is then 1/2 Q0 squared over the capacitance. So my total energy of this thing is equal to a constant, which of course it has to be because for a harmonic oscillator, we know the total energy is conserved. Nothing is leaking energy. So my total energy in this case is simply given by this guy. Okay. What's that? Yeah, because it's going to go away and I don't care. Yeah. Being lazy in my old age is if nobody minds too much. So in this case, if I plot the energy as a function of time, so let's plot our energy as a function of time. So in this case, I'm going to put total energy in orange. Let's put the energy of the electric in yellow, and let's put the energy of the magnetic in green. So my total energy then is simply a constant. So this is going to be my 1/2 Q0 squared over C. Now, in this case, my electrical energy is going to go as a cosine, which means that this guy is going to simply do this, right? Where sorry, that was supposed to be electric. Sorry, make that yellow. Forgot my color scheme. Okay, so this guy's doing this guy. Good, so that's him. And then for the magnetic, that guy's going to start off here and then basically do what? This, right? So this is what the energy is doing as a function of time, or this time across this axis. So again, the energy is oscillating back and forth between the electrical energy and the magnetic energy such that the total energy remains constant at all times. Okay. So this is our LC circuit. So our LC circuit is nothing more than a harmonic oscillator, where this is my charge as a function of time, my current as a function of time, and this is my angular frequency. So let's use this. Let's do a problem. This didn't show up because this thing is not working for some reason, but that's okay. We'll work around it. So this says that we have a 1200 picofarad capacitor is fully charged by a 500 volt DC power supply. Okay, so let's talk about this guy. So we have this fully charged capacitor. So here's my fully charged capacitor where the capacitance is 1200 picofarads, and it's going to be charged by a potential of, what did I say, 500 volts. Cool. Well, that's this guy. Let me unplug him. Oh, 1200, not 12,000. There we go. This guy then is going to be connected at t is equal to 0 to an inductor. So here's my inductor. Good. Or my inductor is going to have an inductance of 75 millihenry. All right. So at t is equal to 0, again, my charge on the capacitor is equal to the initial amount of charge, which we'll calculate in a second. And then my current is simply equal to 0. So from there, what it wants me to do then is find out what is the initial amount of charge. So for part A, we want to know what is Q0. For part B, we want to know what is the maximum current. So what is Imax going to equal in this case? Part C, we want to know what is the period of oscillation and what is the frequency of this harmonic oscillator. And then part D, we want to know what's the total energy. What is the total amount of energy inside of this harmonic oscillator? It's okay. What can't you see, Andre?
Yes, for L.
Oh, so L is 75 millihenries. 75 millihenries. Or chicken scratch, but either way, it's fine. So charge. So let's go back to charge. So going back, what? Last exam, right? Yeah, last exam. The charge is equal to the capacitance times the potential, right? So that means in this case, the initial amount of charge is simply going to be the capacitance times the potential at which it was that charged up this capacitor, which means in this case, this is going to be simply 1,200 picofarads. And remember what pico is? Negative 12, good. So negative 12 farads times 500 volts. So this guy works out then to be 0.6 microcoulombs. So this is my initial amount of charge. Okay. Part B. Part B then says, what's the maximum current? Well, I left this on here, thankfully. My maximum amount of current is simply I0. So I get I0, which in terms of the charge is simply going to be the initial amount of charge times the angular frequency. So it's going to be my initial amount of charge times my angular frequency. Where again, my angular frequency is 1 over the square root of LC. So I'm going to get my initial amount of charge divided by 1 over LC square rooted. So plug in my numbers. So this guy's going to be 0.6 microcoulombs. So that's 10 to the minus 6. Square root of 75 millihenries, which is times 10 to the minus 3, times 1,200 times 10 to the minus 12 farads. We doing okay? What's up?
We always get to ignore like the sign thing in these problems, or
The sign thing?
like you just did the I sub 0. So do we always get
Right, because that's the maximum amount of current.
I see.
Right, but if I was asking you for the current as a function of time or at a specific time, then yes, absolutely, I would use the sign. Yes, yeah. So maximum current is just when the sign is equal to 1. Yeah. I get your question. So plugging all that in, this works out then to be 63 milliamps. So this is the maximum amount of current I'm going to have flowing through my system. What's up, Jamie?
Beginning not 0.
The current at the beginning is 0, but in this case, it's asking specifically at the maximum currents. And the maximum current is when the charge goes to 0. So the first part is t is equal to 0, which is basically when I have the initial amount of charge. Okay. And then the maximum currents will be at 1/4 of the period. So in this case, when it's asking for the maximum amount of charge, it's asking at the time of 1/4 of the period is effectively what it's asking. Because half the period would be, actually, is that quarter of the period? Yeah, quarter of a period, because the full period is when it would go back to its original. Half a period wouldn't be when this one is now the opposite charge. So yeah, 1/4 of the period. Yeah. So it's just asking at different times in this case. Next thing is, what is the period and what is the frequency? So we know the period is equal to what? 2 pi divided by the angular frequency. So it's going to be the same thing then as 2 pi times the square root of L times C. So that's then going to be equal to 60 microseconds. And then we know the frequency is 1 over the period. So that's going to be 1 over micro. So that turns out to be 17 kilohertz. So this then is my frequency. Okay. And then finally, for parts D, we want the total energy. Well, we now know the total energy is simply equal to the initial amount of charge divided by the capacitance of the capacitor. Right? That's what we just showed. So this guy is going to be what? 0.6 microcoulombs squared divided by 1,200 times 10 to the minus 12. So this guy works out to be 0.15 millijoules. So this then is my total energy of my system. Not too bad. Not too bad. Using all kinds of definitions. So cool. So this is an LC circuit. So next one we're going to talk about is an LR circuit. So let's talk about LR circuits. So what's an LR circuit? Well, it's exactly what it sounds like. It's a resistor with an inductor. So let's look at LR circuits. So an LR circuit, let's look at the case where it is charging, which means we're going to add this guy to a battery. So let's say I have a battery here. So this has some potential. It's going to be connected then in series to an inductor. So here's my inductor. There we go. And then that's going to be connected in series to my resistor. This guy. Okay. So this then is my positive side of my battery. This is then going to be what? My negative side. So we're going to have current flowing through the system, which is going to try to do this, right? This is going to be my current. So what's going to happen? So initially, we're going to get a reactive or an inductive reactance, which means that this is going to try to slow down the amount of current. And then this guy is going to dissipate energy, which means that it's going to go to 0 as far as energy is concerned at some point in time. Okay. So in this case, what should we expect? Well, we should expect then that what? Initially, we have no currents running through the system. And then I turn it on. So now I'm going to get currents, which is now building up. This guy's going to cause it to build up slowly. And then eventually, when, again, the current becomes maximum, this thing then is going to act just like a straight wire. You guys okay with this? So let's use, again, Kirchhoff's rules to talk about this guy. So Kirchhoff's rule says that, again, if I start at this corner, let's call that point A. We're going to gain potential from the battery because we're going from the negative side to the positive side. We're going to drop potential across the inductor by a minus L di dt. And then we're going to lose potential over the resistor. So we're also going to get a minus R times I by Ohm's good idea. Then it's equal to 0. Okay. So in this case now, we don't have to worry about charge. The only thing we have here then is simply currents, right? So let's rewrite this thing. Let's get the derivative on one side, everything else on the other side. So in this case, I'm going to get what? Let's call that a minus L di dt is then equal to a V minus I times R V minus Z. That's okay. Now from here, let's now use our separation of variables. So first thing I'm going to do is I'm going to pull out this R. So let's pull out this R. So I'm going to write this then as a what? V over R is I. And then bring the R to the other side. So I'm going to get a over R here. Okay. Now from here, I'm going to what? Bring all the time terms to this side and all the I terms to this side. So this guy then is going to become so we're going to get a di VR minus I is then equal to a minus R over L dt. Okay. And now we're going to integrate this side from the initial amount of time, which is 0, to the final time, and then integrate this side then from the initial amount of current, which is 0, to the final then amount of current. What's that? Oh, we're not. I'm saying we don't have to in this case. Oh, we don't have to worry about it in this case because everything's already in terms of currents. Now, if I wanted to, I could make it in terms of charge. So in that case, then this guy would then become the second derivative with respect to charge. This guy would become the first derivative with respect to charge, and then I would have some sort of constant term, which means I would have a dance in this system, right? But it wouldn't be a harmonic oscillator because there's no linear term in Q in that case. So it's easier to deal with it in this case. Okay. What's that? Is there a sign here? Well, oh, you're saying this should be that? Yeah, that should be that. Good. No, you're right. So an I minus VR. Yeah, good. Yes, 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 yes. Thank you, Andre. Yeah, because I left the negative sign already on the other side. Good. Good, 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 good. So from here, we would then use U substitution. So let's use the substitution to do this. So let's use U then is equal to I minus VR, which means that du is equal to simply di. So the left-hand side then is going to become du over u integrated from, so when I is equal to 0, this is going to be minus v over r. And then when I is not 0, this is going to be I minus vr. Okay? Is then equal to a minus r over L integral 0 to t dt. We doing okay? What's the integral on the right-hand side? Oh, right-hand side, not left-hand side. T, the left-hand side is natural log. So finally, we're going to do natural log on this side. We're going to get a t on this side, but we don't want a natural log because we want I itself. So we're going to have to do an anti-natural log. But what's an anti-natural log? Exponential. Good. So at the end of the day, after doing a little bit of algebra, and skip this part, what you finally get then is that what I of t works out then to be V over R, which is the initial current in this case, e to the minus t over tau, where tau is our new time constant, which is then equal to the inductance divided by the resistance. Okay, so this is then what's called the time constant. Now, this is similar to the same time constant that we had for a, what, RC circuit, right? So this has exactly the same structure. So it acts pretty much the same way, which means that what? At t is equal to 0, my current starts off at 0, and then this guy asymptotically approaches the maximum amount of current, where the maximum current then is going to be simply V over R. So again, in this case, this is going to keep it from building up. So it's going to take time to build up, but once it reaches maximum, this thing is going to act simply like a straight wire. So the only thing that's going to drive the current in this case will be the resistor by Ohm's law. Okay. So this is my LC circuit, or sorry, LR circuit. Sorry about that. And then if I have known batteries, so in that case, in the discharging case, so in that case, my current then is simply going to be equal to the initial amount of current, e to the minus t over tau, where I have exactly the same amount of time constant in this case. So in that case, my current then is simply going to exponentially decay. So this thing's going to start off at I0 and then exponentially go to 0 as time goes to infinity. Was okay?
That's if we like take the battery out.
That's if we take the battery out. Correct. Correct. Yeah, so that would be if we take a fully charged inductor and connect it simply to a resistor. Exactly. Exactly. Yeah, so discharging in that case, no battery. No battery. One more, let me talk about it real quick, and then we'll do an example of this guy, and it's going to be our RLC circuit. So finally, we're going to have our LRC circuit. So our LRC circuit is exactly what it sounds like. We have a capacitor with a resistor and an inductor. So again, in this case, we're going to start off with some fully charged capacitor of capacitance Q. connect that then to an inductor, which is connected then to a resistor, and then we're going to get this guy. Okay. Now, basically, this is the superposition of this guy and that guy, which basically means that with the LC circuit, what did we have? The harmonic oscillator. And then this guy's going to dissipate energy, right? Which means this guy's going to become a damped harmonic oscillator. So in LRC circuits, the charge is still going to harmonically oscillate, which means, again, if this guy starts off positive on this side, the current's going to move through in this direction. So later, this side's going to become then positively charged. It's then going to overshoot, go back. So my current then is going to go in this direction, go back. But every time it goes through, the resistor is going to lose energy due to thermal dissipation. So eventually, all of this is going to go to 0, right? So in this case, my total energy will be a function of time, which will go to 0 as T goes off to infinity. So that's about as much as I'm going to talk about that one, because we did talk about harmonic oscillators or damped harmonic oscillators before, but we didn't do any math for it. But I brought it up because basically it shows up again as an LRC circuit. And again, that's as far as I'm going to go with that. You should know that guy. So let's do a problem involving the other guy here. So this guy. So let's do a problem involving that. So this then says that, what do we have here? So we have at t is equal to 0, a 12-volt battery. I erased my picture. I did. So let's go to here. So now we have a 12-volt battery. So here's my 12-volt battery. Is then connected to an inductor, where that inductor has an inductance of 220 millihenries. And then it's connected to a resistor in series. So here's my resistor, where my resistor has a resistance of 30 ohms. So in this case, it wants us to find, for part A, what is the current at t is equal to 0? That's pretty easy. So part A, what is my current at t is equal to 0? We can answer that right away. What's the current at t is equal to 0? 0, right? So at this point, my initial amount of current is simply 0. Good. Part B, we then want to know what is the time constant? So part B, we want to know what is our time constant. So again, let's do that. So my time constant I know is simply the inductance divided by the resistance. So let's do that right away. So this is then 220 milli, which is 10 to the minus 3, divided by 30. So my time constant then works out to be 7.3 milliseconds. Might as well do these easy parts while we can. Good. So next part then says, part C, what is the maximum amount of current? So part C, I max. So again, I max is simply when the current here, or at least when time goes off to infinity, which means this is our maximum current. So our maximum current by Ohm's law is simply V over R. Okay. So our maximum current then is going to be V over R. So it's going to be 12 volts divided by 30 ohms, which then is equal to 0.4 amps. Okay. Part D then says, how long will it take for this thing to reach half the maximum of its maximum charge? So in that case, we want to know how much time will it take for the current to reach half the maximum amount of current, right? So how much time does it take for that to happen? So let's do that over here. So what do we know? We know now that what the current as a function of time is given this way, where again, this guy is simply I max. So we know the current as a function of time is equal to I max times then 1 minus e to the minus t over tau. Okay. Now what we want is specifically that current is half of the maximum. So let's plug that in. So I'm going to get I max divided by 2 is equal to I max times 1 minus e to the minus t over 10. So what's going to happen to our I max? It's going to cancel, so I don't care about 2 I max. So I'm going to get a 1/2 then is equal to a 1 minus e to the minus t over tau. Now what I want is t, so I'm going to change these two terms. I'm going to bring this guy to this side. bring this guy to the side, which is going to give me a 1 minus a half. But what's 1 minus a half? A half. Good. Not a trick question. Good. So in this case, I'm going to get an e to the minus t over tau is equal to then 1/2. All right. Or let's invert that. So I'm going to get a et over tau is equal to 2. What I want is the time. So I have to get rid of the exponential. How do I get rid of an exponential? Natural log. So finally, we're going to get that time is equal to the time constant times the natural log of 2. Okay. So look at my numbers. What I get in this case then is the amount of time it takes for this thing to reach maximum or half the maximum amount of current is 5 milliseconds. Bless you. That's okay. Next up, part E. I'll do E here. So part E then says, at this instance, we have the, oh, sorry, go to the question, there we go. So it says, at this instant, at what rate is the energy being delivered by the battery? Okay, so I want to know at this time, so at t is equal to, in this case, 5 milliseconds, or when the current is equal to half the maximum current, what is the power being delivered by the battery? Okay. So what do we know? We know power is simply going to be the current times the potential. Okay. This is our definition of power. So in this case, this is going to be simply equal to half the maximum current times simply the potential. So we know our maximum current is 0.4 amps. We know our potential is 12 volts. So half of that then is going to be 0.2 times 12. What's 0.2 times 12? 2.4. Good. So this guy is going to be equal to 2.4 watts in this case. Everybody's okay? And I'll leave it there. We'll call that the end of it. So we got about 4 minutes. Okay, so that's it. We are now officially done. So tomorrow then we'll do our review for Monday's exam, and then I'll give you the last remaining group assignments, which are up on Blackboard, but they all have to do with Faraday's law. We'll talk about those. And then, yeah, we'll pretty much be done. I did post the outside extra credit finally, so that is up on Blackboard, so you can work on that guy. I'll give you a hint. It involves Faraday's law and inductors. All the stuff that we just finished talking about. And yeah, that's pretty much it. But I don't know if I should be nice and tell you guys something. I will be nice and tell you guys something. So technically, if you decide to Google this problem and you find this solution that apparently depends on online, it is absolutely wrong. Don't do that. Okay, it completely changes the problem. Makes it about as trivial as possible, so there is no flux going through it. So apparently this thing is on Chegg, and you have to like the solution before you can actually download it, and it's completely asinine, and it's wrong. Don't be that person. This is the outside extra credit. Yes. So don't be that person. Cool. I'll leave it at that. Okay. Do swidania. Auf Wiedersehen. Tschüss. Arrivederci. Assalamu alaikum. What's going on? Yep. Oh, so all we're saying is, so once we write it in this case, we just have to identify the fact that the second derivative of the charge is the same thing as acceleration. And then the charge here will become the same thing as the distance. So matching these things here, because this is our definition of how we find the angular frequency, then if I match this as A, and then I match this guy as X, then whatever shows up after the negative multiplied by the X is the angular frequency squared by definition. So we're just using definitions from what we did 1,000 years ago. Just identifying those things.
It's just that you've written this as A is equal to, so I thought it'd be EQ over DP, just W, and then it's squared would be.
Oh, right. Well, that's this one. So here I was just identifying that this guy is A.
Okay.
So I was just making that connection between the two. Cool. So that's all I was doing here. So I was saying, so this guy here we can use as A, and then this guy here we can use as X.
Okay.
Yeah, so I was just identifying those so we can make the one-to-one correspondence.
All right.
Okay, kind of makes sense. What's up? No, sorry, I forgot to send an email about that. No, today is a makeup lab day. So yes, so if you have no makeup lab, then I'll see you tomorrow then. Sounds good. Okay. Fine, fine, fine.
Every time someone asks you, they have lab